I welcome you all to the Spark Research YouTube channel. This is Dr. Vichand, Assistant Professor in the Department of ECE, and here is the another session for this particular course, Signal Processing. And in this session, we are going to talk about the analysis of the discrete time and signals and system. So this part belongs to the Unit 4th only, and this is the second and the last part of this Unit 4. So in this session, primarily we are going to talk about the window technique, how to design the finite impulse response FIR filter using this window technique, right? And we will look into the rectangular window, Hanning window, Hamming window, and Blackman window. So these are the types of the window that we are going to talk about it in this session. So here is the syllabus, you can check it, and here is the contents that we are going to talk about in this session, right? So question number first is coming while we are talking about this FIR filter, then what is the importance of this Windows method? Why are we keep on talking about this? So major thing you can understand it here, like here first see whenever the filter we are designing, this is the low pass filter, whenever we are designing, initially it have the multiple ripple, right? So we are trying to design the filter which have the a smooth curve, right? So this is the our primary target. So here you can see this is a smooth one, and some more detail about it. Here suppose if you are, this is the actual your magnitude graph. So here if you'll see the filters, it will have the zigzag. Why is this so? Because of this the impulse response of your rectangular function. So whenever you will have the Fourier transform of the rectangular function, it will be sinc function, and due to that these type of the ripple will come. So this is called nothing, this is called the Gibbs oscillation, right? So this is the one of the important term. So problem is this, the rippling, and how can we remove this, right? So in order to, we cannot remove, but we can overcome, right? So in order to overcome this Gibbs oscillation, we are trying to talk about the different window technique. So using the window technique, we will design some type of the filter so that the filter will have a smooth curve, and the the within the cutoff frequencies you can that it will pass the some particular wavelength or particular frequency, right? So this is our target. So in order to do so, in order to achieve the smooth curve, we are trying to design the multiple types of the filter, right? So multiple types of the window we are using so that our curves will be smooth, right? So let's see. First type is your so that is why we are talking about the window method. So if you recall that here Gibbs oscillation originate from the abrupt truncation of the infinite length coefficient sequence. Then it natural to seek window method. So what are the window methods we are going to take here? So like HWN, that is window, is equal to H of n into W of n. So H of n is your actually output, but we are going to multiply with the Wn, right? So that will be the final for the transfer function of your window technique, right? So we are going to find, so instead of the Wn, we are going to use the multiple types of the window, and that is depending on the situations, the filters that you want to do design. So for like here are the types of the window you can see here. So out of these five in our syllabus, we are going to talk about the rectangular window. For this rectangular function is equal to 1, like already you know, this is the type of the rectangular function where it will be 1 for m is in between minus m to plus m. So m is your nothing, the length, right? Length of your rectangular function. And triangular, we are not going to learn it here. This is 1 minus n by m. And Hanning, here in this syllabus it is there, Hanning your window function is nothing, zero point 0.5 plus zero point 0.5 cos n pi by m. So and Hanning it will be 0.54 plus 0.46 cos of n pi by n, and Blackman is 0.42, and so you can see here, okay? So of course It's depending on the the situations, the questions, you can use the type of the window. Here you can see here the dotted one, these are representing the different types of the window, right? So Henning is representing the solid and solid line, Hamming window the dashed line, and the Blackman window, right? So all these type of the windows are there, so you can check it. Okay, so before that, what are the types of the filters we are going to design? The low pass filter means it will eliminate the the high frequency, and high pass filter means it will pass the high frequency and it will eliminate the low pass, right? A low frequency it will not pass. Similarly, band pass will pass the only selected the frequency, this one or this one or even this one and this one, right? And band reject means it will reject, it will not pass this one, and also it will not pass this one, and this one, and this one also it will not pass. So like that, the portion you are not passing, that is band reject. Okay, so here now we will see FIR filter design using the rectangular window technique. So this is the rectangular window techniques, all right? So this is your so for each of the the impulse response, you can have the multiple of sinc functions, and if you add, then you will find finally you will get these type of your frequency response. Here the the ripple is there because of this gives oscillations, right? So our target is to make it more smooth and more smooth, right? So that is why we are using this window technique, and already we have seen that the equations for the window technique, right? So let's see one by one. First window is your rectangular window, right? So here is the WN rectangular window. So important thing is that you have to remember this W, right? So this is nothing, this is one only for M, the 0 to M minus 1, and in this case magnitude response is nothing, sinc function, right? Why is this sinc function? Sin x by x, because the transfer function of your rectangular function is nothing, the sinc function. Here is the the magnitude plot. So magnitude you can plot, that is 20 log of, and the rectangle the W of e to the power j omega t, that is this one with respect to the different frequency, right? So put the value of omega and get the output. Okay, so what is the important? So abrupt truncation of the sink then causes Gibbs phenomena. Here you can see the Gibbs like multiple oscillations are there, but based resolution, this is the very simple technique to design, but the ripple is very high, so vast ripple is there in this case. So okay, so we'll design the next type of the window. So Hanning window, you can see here. Here ripple is a little bit less, right? So a smooth tapering is here. Now in this case, so a smooth tapering is here. Reduce ripple, like here ripple is reducing, but still ripple is the somewhere it is there, and slightly loss in sharpness, right? And what is that major thing is that you should know about this W of n, right? What is this Wn? That is equal to half of 1 minus cos of twice pi n divided by m minus 1. M is nothing, your number. Here you can see total m, that is how many numbers, right, of the FIR impulse responses are there. So m is like you can count. In the previous the session we have discussed about the m, so it was 9, right, if you remember. So you can check that previous video also. I will drop the link in the description section, right? And corresponding to this, you can find in the frequency response, right? So this is in the time domain, that is WFN, and in the frequency domain, you can rewrite the same equation that is in the that is the Hanning window. Once if you have the window now, then it is very easy to get the final output. You can multiply the in the time frequency domain, that is the window along with your transfer function of your filter. Okay, so let's continue to talk about the another window. So here is your Hamming window. So W of n is here, that is 0.54 into minus 0.46 cos of twice pi n divided by m minus. Again, this is in time domain, and here is in the frequency domain. So main lobe width is equal to 8 pi by m also. So here this is 8 pi by m. And again you can check here the ripple is a little bit lesser, right? And your Hamming window will looks like this type of the Hamming window. So this is optimized to reduce first lobe and widely used in practice, and good balance in between the ripple and transition. So ripple is like less, but still it is having but less, very less, right, compared to the previous windows technique. Okay, so last window technique is your Blackman. Just remember this formula, this is important one only. So this is the nothing, your window 0.420 minus 0.5 cosine function and plus 0.08 cosine function, right? Again this is the Fourier transform of your same uh, window, right? And so main the width of your main lobe is nothing, 12 pi by 8. And strong as smoothing, you can check it here, very low side lobes. So side lobes are very low, and definitely this is a smooth. And best for high attenuation requirements, right? So here smooth is more curved, so that is why Blackman is separate one. Here is the overall one. So if you remember, you can check it, the rectangular, then the Hamming and the Hanning and the Blackman. So all the are these are in the time domain, and you can also check in the frequency domain, right? And the width, main width loop for all the rectangle window function is given, and the minimum stop band attenuation is already given, and peak value of the side lobe is also, right? So you can check all these values. Okay, so now we'll take the some questions based on this. So if you'll solve the some questions now, it will be very easy for you to understand the window technique. So what is the question here? In this question, we have to design a low pass filter. LPF means we are going to design a low pass filter using rectangular window, right? So why are we using rectangular window? We'll have the other windows possible, right? Hanning, Hamming and Blackman, right? For the desired frequency, right? For the low pass, and given the omega c is equal to minus of pi by omega c is equal to pi by 2, and take m is equal to 11. So number of impulse response, that is m is equal to how many? 11. Find the values of hn. So first question is that we have to find the values of transfer function, that is h of n, right? Now also we have to plot the magnitude response. So let's find out the h of n. So in order to find out the h of n, we have to find out the what, h of d of n, right? First, that is the what is the transfer function of your LPF, and then we will find out the transfer function of the h of like your rectangular window, and then we will multiply and we'll get the h of n, right? So that is the way. So let's find out the transfer function for your LPF. So it is already given, hd is equal to nothing, e to the power minus j omega t. Why? Because your this is your h of this is your low pass filter, and minus omega c to omega c, it have the value of this one, right? So now rewrite, and what is the tau? You can find actually mid one. So m is already given, m is nothing, 11, right? So put the 11 minus 1 by 2 is equal to 5. So this is 5. So now take the inverse Laplace transform of h of d, already given. This is your h of d. So how will you get the inverse transform? Multiply by e to the power j omega n, and integrate it over minus pi to pi. Why are we integrating minus pi to pi? Because your time period is in between minus pi to pi, and in between pi by 2 and pi, of course, it is 0, right? So then integrate, and you will get h of dn is equal to nothing, 1 by pi of n minus pi, and this component, right? This is nothing, e to the power x minus e to the power minus x divided by 2j. So this will be something like sine theta. So your filter is your hdn, that is sine x and divided by x. So this is again looks like the sinc function. Of course, it was very well known because our LPF is nothing, rectangular function only. So for n is equal to 5, of course, this will be not valid. Actually, it is symmetric. If you will check, impulse responses are symmetric because m is equal to total 11. So it is symmetric at mid, that is fifth one, right? So here h of d is equal to, already we have this tau is equal to, we are converting n minus here, right? So n minus 5. So now if you will try to find h of 5, of course n, that is 5 minus 5, it will be 0. So if we'll use the L'Hospital rule, you will get the s at the 5 n is equal to 5, your function will be your 0 point, your it will be the 0.5, right? So here we got the h of d at 0 at 5. Now you can put the values and in this equation for, and in order to get the value of 0, in order to get the value of 1, similarly 2, 3 and 4. And why are we trying to get all these values? Because it has given that m is equal to how many? Total 11 impulse response are there in order to convert our Laplace transfer, the full filter, right? So here how many? 1, 2, 3, 4, 5, 6, right? So total 11s are there. So what are their values? So that we are getting. So we got the values, right? So these are the values for 0, 1, 2, 3 and 5 already. You can check 5 is already center, now located at center. So this is 0.5, right? So already we got it. And if you'll check, then 6 and 4 both have the same values, and 7th and 3rd again both have the same values, and 2 and 8 again same values, then 9 and 1 again same values, and h0 and 10 both have the same values. What does it mean? Both are symmetric, that we have already discussed for odd symmetric, right, in our previous session. Now after getting the value of your hn, now you can move to find out the plot for your the h of j omega, that is the magnitude plot. So first question is over. Now second question, right, as per that. So rectangular function, that is a window is given, that is w equal to wn is equal to 1, right? So now our objective, the impulse response of the symmetric chord hz is equal to, if you remember, for odd symmetric, right? So this is at n is equal to 5 and the remaining this one, right? So transform. So put the values h of 5 z to the minus 1 and the remaining you will get this equation, right? So for h0, h1, h2, h3, h4, h and total 11 already it has been given in our question, that total impulse responses are how many? 11, right? So you can add all this. Now in order to further solve this, like no need to add all this, you can use the odd symmetric. So first this is for n is equal to 5, and for remaining you can use the symmetric. So m minus 3, that is 11 minus 3 divided by 2, and you will get this, right? So you get the value of h of j, right? So here is the multiplication of both h of d and into the rectangular function. Okay. So finally, if you put the values, you can get the value of the h of g omega. That is your the transfer function values with respect to the omega, that is frequency, and then you can plot it. And if you plot, you will get this type of the response. So this is the second question. Similarly, here is the another questions. Here you have to design the high pass filter using the Hamming window. Here in the previous question it was a rectangular window. Here the question is the Hamming window. So in that case, if you remember the what is the equation for the Hamming window, it will be very easy. Cutoff frequency is given, and filter coefficient, given the cutoff frequency, the cut of the filter coefficient hdn for, so request for the digital pass, and given by omega c is equal to this, and take m is given, your m is say 1 in this case, right? In the previous case it was 11, right? So get the HDN already given. In the previous question it was low pass filter. Now HDN is given. So find out the tau. Again the same things. Find out the H of DZ and then take the inverse Fourier transform and get the value of H of DN. And after getting H of DN, you can put the values of N and get the value of H of N. So this is the very simple way, right? So these are the steps. Further, in order to get the magnitude response for this, multiply, the solve it using the window formula. For Hamming case, this is, the for Hamming case, you can apply the window. This is again the odd symmetry, so solve it using the odd symmetry first in between at the remaining two and get the value of h of j. Similarly, here is another question for Hanning window, and here again the what is the question? Design a BPF, that is band pass filter, using the Hanning window, and the remaining things omega and c, these things are given. So again, take the inverse transform of your HDN, which is already given in the question, and then find out HDN and then put the values and multiply using the h of n, that is using your hand, the your window function. So here multiply your window with the hd and you will get the, so here is the multiply with the h of dn into the omega n, you will get the final values of the h of n, right? And then you can also get the value of the conversion. By conversion, you can get h of g omega and put the values and you can plot the magnitude. Here is another question, right? So similarly you can solve. So major thing is that you can get the crux is that first get the HDN, that is the frequency, the time domain transform frequency, the transfer function, time domain transfer function, using the inverse transform. Why is inverse transform? Because these wave, these rectangular functions are given in the time, sorry, frequency domain. So first, how will you convert in the time domain? After converting in the time domain, why are we converting into time domain? Because like we know the window in time domain, right? After get, then only we can also get the impulse response in time domain. So actually our target is to replace it by the some impulse response, right? So like that. So in time domain only in impulse response, otherwise in the frequency domain this is your rectangular, already you can see. So get the h of d of n. So how will you get? Use this for inverse Fourier transform and get the value of h of dn, and then get the window. Like here window is for rectangular, window is 1. For other cases your window is different one, and then multiply and get the value of h of n, right? So h of n will be your h of dn, that is the inverse Fourier transform of your, the functions given in the question, multiply with the window and get the h of n, put the values of n is equal to 0, 1, 2 and all those and get. Also you can get the plot for your magnitude response. So again, convert in the frequency domain of your sequence whatever you got, that is impulse response, and get the final value of your h of z by putting the value of the frequency. Okay, okay, that's all in the session. Thank you to join.